Hello everyone, welcome back to our free calculus algebra online course this summer. Today I'm going to cover section 2.6, zeros are polynomial functions. I claim that this is the most important section of chapter 2 in our course. Second, I claim that the textbook provide a lot of theorems in this section, and I won't be able to cover all the theorems because some of those I personally believe is really not worth as a theorem. So what I'm gonna go over today in this section is the three biggest theorem in algebra, or at least about polynomial, and it's the most useful one. It means that the other theorem, even though they call it a theorem, it's just like a little signals to look at the polynomial. And I urge all of you, please read the textbook for your full understanding of all the materials that we'll cover. But in our section today, as I just mentioned a couple of minutes ago, I will go over the three most important theorem in our section, in our chapter 2. Okay? And first of all, in talking about zeros of polynomial, we're going to extend the concept of the value of 0. We're not going to stop at real numbers anymore. In this section, we're going to extend them on to the complex numbers. So let me give you a brief review about complex numbers. Okay. Complex numbers. We start with something called the imaginary number. We denote it by a letter I. With this definition, I is equal to square root of -1. Right? In real numbers, we don't have square root of a negative number. We only accept square root of non-negative numbers, meaning positive or 0. But in here, we define just kind of weird thing at first. Define a number I. Okay, I stand for imaginary. Square root of a negative number, and I believe we think of it, this is only happen in our imagination, so we call this imaginary number. Or equivalently, we can square up both sides. People can define this way: I squared equal to -1. You see, some number only happen in our imagination that we square up equal to -1, and that's called the imaginary number. Now, together with the real number, we can construct the complex number. Okay, so the complex number is defined this way. Complex number. It's number of the form a plus bi, where a and b are real numbers. And a here is not going with I because the real part, and b goes with I because the imaginary part, imaginary. Okay, so in general, there are two parts of a complex number: the real part and the imaginary part. Okay. Example: you have, say, 3 plus 2i. So a is 3 and b is 2. A plus bi, 3 plus 2i. Okay. Or 2 minus 7i. So a is 2 and b is -7. How about just 5i? And that means what? 0 for A and 5 is for B. Think of it this way: 0 plus 5i. And similarly, what if I give you 6? This is a real number, right? So this, you can think of as 6 plus 0i. And you have a complex number. So the other example, you see what? Real numbers now are just a part of a bigger set, which is called complex numbers. All right? Now, introduce one more term about complex number you will see in this lecture today, in this section today, called the conjugate. The conjugate of a complex number is a new complex number that we change the sign of the imaginary part. So if you have the number, say 3 plus 2i, then the conjugate of this is 3 minus 2i. You see what I've done to get from the first complex number to the second one? I changed the sign of the imaginary part. Okay, keep in mind that we only change the sign of the imaginary part. So 3 plus 2i, now 3 minus 2i. The pair right here, because the pair of conjugates. Are we good? Second one, I got 2 minus 7i. The conjugate of this will be 2 plus 7i, right? And then 5i of the third one. Then the conjugate of 5i is negative 5i. And the last one right here, 6 plus 0 actually is just 6. Oops. Then we don't have the imaginary part. We change the sign of the conjugate part is still 6. So pretty much you can say that the conjugate of a real number is 7. So far, so good. Now I think we're ready to get into our section 2.6. As I say, I will cover the 3 biggest and 3 main theorems, the real theorems of this section. And one more time, I'm urging all of you to read the textbook for all other things that I won't cover in our clip today. Okay, number 1, talk about the fundamental theorem of algebra. Okay. So first of all, we let f of x be a polynomial function. Polynomial function of degree n. There's one condition, n is greater than 0, so we don't count for constant. Degree 1, 2, 3, okay? And the version of this theorem in the book says a polynomial function of degree n when it's greater than 0 will have at least 1 0, okay? And that's more general, that's more powerful, we understand that. Well, let me rephrase this. Let me write it in a simpler version. Right? It's equivalent, it's the same, it's just I believe it's going to be easier for you to understand and to get the whole picture if I write it this way. And it's the same, okay? The book way of writing is more compact and it's better, okay? But the way I'm going to write it is going to be easier for you to get the whole. Okay? So let me write this way. F of x be a polynomial function of degree n. The book says that's going to be have at least 1 0, and I'll say it this way. Then f of x has exactly n complex zeros. Complex zeros. Okay. Saying as it's got 1 0 is good enough because after having 1 0 we do synthetic division, we can find another 0 eventually all the way to the end. You still have n complex zeros. So you don't have to write, we ask mathematician, we write the theorem, we gotta write it in the most compact way. But since we don't do research on that, we learn in math, so we try to write the way that hopefully it's get to every one of you easier. Okay? So I'll say it this way. A fundamental theorem of algebra say that's polynomial of degree n will give you exactly n zeros. Period. Okay? N complex 0. Okay? So degree 5, you know they're going to have 5 complex 0. Degree 1,000, going to give you 1,000 0. Degree 0 gives us 0 0. Okay? No 0 at all. That's the third theorem called the fundamental theorem of algebra. It is about polynomial function. Okay? And the same condition right here, degree n or n greater than 0. We move on to the second theorem called the factorization theorem. Before writing down, let me try to explain the idea of this a little bit. The function f of x, the same condition right here, function f of x is a polynomial with degree n when n is greater than 0. And it has n complex 0. Let's call the n complex 0 as n complex zeros. Let's call those zeros a C1, C2, C3, all the way to Cn. And what we learned before about the 0, if a polynomial have a 0 of C, then it's going to have 0 equal to C, and it has a factor of x minus C. Was that right? And if C is a real number, then we talk about the x intercept, but we only care about 0 and linear factors. Okay, So if a polynomial got n0, c1, c2, c3 is going to have n factors. X minus c1, x minus c2, x minus c3, da, 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 all the way to x minus cn. And the second theorem said that if a polynomial f of x with degree n, then it can be written as f of x equal to, oops, I forgot something in here, a times the product of n linear factors, x minus c1, x minus c2, x minus c3, all the way to cn. Okay? And brought in this way, you can have a better look at the function, polynomial function of degree n. Instead of writing in general, you can factor out as n linear factors, where a is the leading coefficient. Okay? So in a nutshell, the second theorem, called the factorization theorem, says that if you have a polynomial f of x of degree n, then you can write f of x of the form a leading coefficient times n linear factors, x minus c1, x minus c2, x minus c3, all the way to x minus cn, where c1, c2, c3, all the way to cn's are the zeros of that polynomial. Okay, that was the second biggest theorem. And let's move on to the third one. The third theorem, called the conjugate pairs theorem. Okay. The third theorem says that if C is a complex zero of f of x, then the conjugate of C is also another zero of f of x. And this is a pretty important theorem as well. We're saying what? You have a complex zero, then you know another number, another complex number, which is also a zero for the polynomial. So somehow, say for example, you have c1 is equal to 2 minus 3i. This is the zero of the polynomial. Then without learning any further, you immediately know that c2 is equal to 2 plus 3i will be another zero for sure for the polynomial function. And by the way, in our section today, actually in our entire course, we talk about polynomial function with real coefficients. Okay, real coefficient, and that's good enough. We don't talk about complex coefficient yet. It's going to have this property. All right. Now let's see some application, some use of the three biggest theorem. But before we move on to that, next items for the section, let's recall three. The first theorem say what? Called the fundamental theorem algebra say what? Polynomial of degree n give you n zeros. And if we call the n zeros n complex zero, c1, c2, c3, the second theorem say what? Function f of x can be expressed or can be written as leading coefficient times n linear factors, x minus c1, x minus c2, all the way to x minus cn. And then the third theorem, the conjugate theorems, conjugate pairs theorems, say this: if C is a complex zero, then the conjugate of C is also another zero of the polynomial function. Okay. Now let's talk about some application. Okay. I'm going to give you about two examples to show you two typical types of problem that you see in this section. And one more time, please take a look at our textbook on my math lab. That's provided when you register for the course. Right? It's on my math lab to find the other things about this section, okay? Because you guys are gonna need to do the homework. So I about number 4, some applications. First type of application is construct a polynomial given some condition. So let me write down first example. Construct how about find, make it easy. Find a polynomial function f of x of degree 3 that has zeros x equal to 2 and x equal to 3i. Okay? So I'm giving you some information about this polynomial function. I gave you that this is a polynomial function of degree 3, and I give you 2 zeros, x equal to 2, x equal to 3i. According to what we just learned a couple of minutes ago, polynomial of degree 3 is going to give you 3 zeros. Okay? That's 3 zeros. 3 zeros. You got x equal to 2, x equal to 3i, and you are missing one. We got to find the third one. And now I'm going to use the third theorem right here, got the conjugate pairs theorem to find the third one. I see that this is real number, so there's no conjugate to talk about. This is 3i. The conjugate of 3i is x equal to negative 3i. Okay, by the conjugate pair theorem, this third one will be another 0, the third 0 of the polynomial function. And that's all the zeros that the function may have because of the first theorem, polynomial of degree 3, had 3 zeros. You found them. And the second theorem say what? You can rewrite the polynomial functions f of x equal to the leading coefficient and then times x minus c1, x minus c2, and x minus c3, right? I wrote x in there, means c1, c2, c3. Oh, I forgot something in the problem, so I have to provide you one more piece of information. I have to give you the leading coefficient. So let me cheat a little. I'll put it here. With leading coefficient equal to, make up a number, how about negative 2? All right, so put it in, because you're going to need that to find the whole thing. All right, so look at me as f of x equal to negative 2 times x minus 2 times x minus 3i times x minus negative 3i. You see? There's a leading coefficient, x minus the first 0, x minus the second 0, and then x minus the third 0. And I claim later on, if you master this, you practice enough, you don't write minus 3i, negative 3i anymore. All you can do is simplify it right away, and then write x plus 3i. Okay? And then multiply them all out, simplify polynomial, you have the answer. Let's do it. Okay? So f of x is equal to negative 2 times x minus 2, x minus 3i, and x plus 3i. You can multiply any two factors among those two together, that's fine. But I claim that it would be easier if you take care of the pair of conjugates first, because it's going to help you to cancel out the imaginary number I. Okay? So I'm going to FOIL this thing out. I'm going to leave negative 2 times x minus 2 alone. FOIL. X times x is x squared. X times 3i is plus 3ix. And then negative 3i times x is negative 3ix. And negative 3i times positive 3i is negative 9i squared. Here comes a very typical mistake I've seen over and over when I see you guys do the work. This is I squared, okay? I times I, you got I squared. Negative 3 times 3 positive, so this is negative. I mean, so negative 9I squared, not just a single I. Now, keep in mind that I squared is negative 1 by definition. So, negative 9I squared is no more than negative 9 times negative 1, which is plus 9, okay? So, we have what? Negative 2x minus 2 times x squared. You see what happened to the middle two terms? Cancel each other out. And then you have plus 9. You see what happened after this? No more I. keep going. Negative 2 out, 4 this out, we got x cubed plus 9x minus 2x squared minus 18. I say 18. Negative 18. All right. Distribute negative 2. Let's rearrange the sum at the same time. So negative 2x cubed, negative 2 times negative 2 plus 4x squared minus 18x and plus 36. You have the answer. And this is our polynomial f of x of degree 3 with leading coefficient negative 2 and has 3 zeros, 2, 3i, and negative 3i. Let's try another example. Let me change a little. I'm going to change just about just one thing. Instead of 0, 2, and 3i, about 1 plus 3i. And I'll keep everything the same. Okay? Just the same type. I'll just repeat another example. Just example one more time. Just want to make sure that you guys get it. You have a chance to see the type of problem twice. And that's better for you. Okay, so the 3 zeros are, the first 0 is 2 already. Okay? The second 0 is 1 plus 3i. And according to the conjugate pair theorem, the third 0 will be the conjugate of this one, which is 1 minus 3i. Those are 3 zeros. So now, how do we write the polynomial function as product of linear factor? Negative 2 right here for the leading coefficient, and the first 0 is x minus 2. The first linear factor is x minus 2, is associated with the 0, x equal to 2. Very good. Now, for the second factor, it's going to be x minus 1 plus 3i. And you see the way I wrote it. 1 plus 3i in parentheses. X minus the entire 0. Okay? It's very important that you have in parentheses because later on you need to distribute a negative sign into the two terms. Okay? For your safety, you do an algebra. And then similarly, the third factor is going to be x minus, and then parentheses again, x minus 3i. I'm sorry, 1 minus 3i. All right, and of course simplify and then factor out, you have the answer. Let's work it out. So the main thing I try to bring up in this example is how you write the linear factor with complex 0. X subtract the entire zeros in parentheses. Okay, let's work it out. So f of x will be equal to negative 2 times x minus 2 times x minus 1 minus 3i times x minus 1 plus 3i. Yeah. X, distribute a negative sign to the two terms in parentheses, you got minus 1 minus 3i. Similarly, x minus 1 and then plus 3i. Now let's FOIL everything out. Again, working with the conjugate pair would be a very good strategy, so I'm going to take care of this. Okay? X times x is x squared, x times negative 1 is negative x, x times 3i is 3ix, and same thing, move on to 1, negative 1 times x is negative x, negative 1 times negative 1 is plus 1, negative 1 times 3i is negative 3i, and then move on to the third term, negative 3i times x is negative 3ix. Negative 3i times negative 1 is positive 3i. Negative 3i times positive 3i is negative 9i squared. Alright, one more time. Negative 3 is negative 9. I times I is I squared. Now what? Simplify, combine the like terms. Negative 2, x minus 2. This is x squared. Negative x with negative x is negative 2x. Right, 3ix minus 3ix cancel out, minus 3i plus 3i cancel out, and this one right here, negative 9i squared, I squared is negative 1, so negative I squared is 9 right here, 9 together with 1 is 10. Alright, now FOIL one more time, negative 2, x cubed minus 2x squared plus 10x, negative 2x squared plus 4x, and then minus 20. Alright, now combine the like terms. We got negative 2x cubed, negative 4x squared plus 14x minus 20, and multiply everything by 2, distribute the negative 2, negative 2x cubed plus 8x squared plus 28x minus 28x would be, because I multiply by negative 2, and then plus 40. That will be the final answer. Okay, let me check with my algebra. I may make mistake on the way, but the idea is right there. Hopefully I didn't make any. So, the other two examples, you guys see the first application of this section is to construct a polynomial of some degree with leading coefficient, and they give you some zeros, then you'll be able to find the rest of the number of zeros, and you can put them all together, simplify, do some algebra, and have the final answer. Be very, very careful when you do algebra, because if you make one single tiny mistake somewhere, then you will not get to the right answer. Okay? But the idea is going to show on the board. All right. I'll show you the second type of application. And I claim that the second type of application, you guys have seen it already. So I'll just go over with one example, one typical example. It's enough, okay, to get the second type of application. Number 2, find all zeros of a polynomial function. Okay, so in this topic, we're going to give you a polynomial function. They ask you to find all the zeros of this polynomial function. So let me start with an example. Say f of x, polynomial function. Okay, f of x equal to, make it up, 2x cubed plus 7x squared plus 4x. Let me see if it's right. Yep. And then plus 1. Plus 6x then. Plus 1. I'll just make an example. Okay. And this is the polynomial of degree 3. Leading coefficient 2. The question asks you to find all the zeros. According to what we learned, polynomial of degree 3 going to give you exactly 3 zeros, 3 complex zeros. Find all, say, more precise, complex zero. Could be real, could be complex number. Okay, it includes everything. All right, and the strategy to tackle this type of problem is to come back to a test that we learned before. We call the rational zero test. You take the last coefficient divided by the first coefficient. Rational zero test. Okay, that's 1/2, and we are really trying our luck in here. Hopefully, we can find the very first rational zero before we can move on. So we're looking for all the factors of 1, I only have 1. All the factors of 2, I got 1 and 2. So I have a couple fractions, 1/1 and 1/2, plus or minus, plus or minus. Okay? So I have to try 4 possible rational zero. In here, hopefully I can find a good one. Alright? And instead of trying all 4, I think I mentioned last time what we can reduce our work, our amount of work, by looking at the coefficient. Hopefully this gives you some hint. And in this problem, I gave you what? All positives.